Okay, good. So if you remember the last day, we were discussing, the possibility to find which is the generating function of the canonical transformation, which is the identity transformation. That means the transformation in which you change nothing. You go from Q to Q prime, which is the same as Q, and P to P prime, which is the same as P. And the reason why we want to do this simple thing is because we're going to start, looking at perturbations, small perturbations with respect to this identity canonical transformation. And for that, it is, a good idea to change variables from Q and Q prime in the generating function to Q and P prime. Because the function, the generating function, which has Q and P prime, obeys these differential equations, and that makes, the construction of the identity canonical transformation very simple, right? Because we find that f has to be such that the derivative with respect to Q, function of Q and P prime, has to be lambda P. In general, this is going to be a function of time also. But in practice, we are not going to complicate our life by making it time dependent. So we're going to forget about the time dependence. We don't need that, as you will see. And the other differential equation is partial of f with respect to p prime, function of p, function of q, p prime, and t. Again, is not going to be a function of t. This has to be q prime. So if we choose f of q and p prime equals to q p prime, as simple as this, with unit valence, so we don't even need a valence, then it is immediate to check that, of course, what is the derivative of f with respect to q? The derivative of f with respect to q is p prime, but, on the other hand, it is lambda p, which is p. So that means that, we go from p to p prime. So this justifies that we're going to p prime, which is the same as p. And the other one is partial of f with respect to p prime. And if I take the derivative with respect to p prime is, of course, q, but q is the same as q prime. So this is telling us that we go from q to q prime, which is the same as q. So it is the identity canonical transformation as we want it, okay? Good, so we already have it. So now that we have the generating function that does this, we got to start, studying the interesting part of it. Okay, so let's study a canonical transformation close to the identity. Okay, so not just this, but just a small variation with respect to it. And so this is going to be controlled by a small parameter, which I'm going to call epsilon, which is going to be much smaller than 1. So this is going to be the parameter that controls how much I, diverge, how much I go away from the identity canonical transformation. So my generating function, f of q and p prime, is therefore going to be q p prime plus this small parameter, a general function of q and p prime, okay? Where epsilon is very, very small. All right? Okay. Now, in general, we're going to keep a certain time dependence here because nothing is going to change, okay? Now, let us see what the equations are now, the partial differential equations are now for this generating function. So now, since there is this g here, things change a little bit, right? So this is going to be partial of f with respect to q, right? So this partial of f with respect to q is p, And if I take the derivative of the f that I just constructed, this is, of course, p prime plus epsilon partial of g respect to q, which is in principle a function of q, p prime, and t. So this says that p prime is p minus epsilon partial of g respect to q of q, p prime, and t. But to first order in epsilon, so let's do this thing to first order in epsilon, I can forget about this prime here, right? Because the difference between p prime and p is of order epsilon. So if instead of p prime here, I put p, the difference is of order epsilon times epsilon is order epsilon squared, okay? So I'm going to forget about this, right? So even though here there is a p, I'm sorry, there is a p prime, there is a p prime, I'm going to forget about the p prime, okay? And this is going to be okay up to order epsilon squared. So that's one of them. And the other one is q prime, right? Q prime is partial of f with respect to p prime. And for this function here, if I take the derivative with respect to p prime, this is, of course, q plus epsilon partial of g with respect to p prime, function of q, p prime, and t. And that means that q prime is q plus epsilon partial of g with respect to p prime, which is a function of q, p prime in principle, and t, right? But again, since this is already of order epsilon, here I can just, forget about the primes, okay? And this is going to be okay. This is going to be true up to order epsilon squared. Okay? Any questions up to now?
No.
Okay?
No.
So we're going to call g of q, p, and t, this function that measures, the deviation from the identity, we're going to call this thing the generator of the canonical transformation. Not to be confused, not generator, not to be confused with the generating function, right? The generating function is f. F is the generating function. Generating function, as we have been calling it, since the very beginning, generating function. Whereas this g, which is the deviation, it measures the deviation from the identity, is the generator of the canonical transformation. And the reason why we call it generator is not a coincidence. Is for the same, as you will see, is for the same reason we also call generator to something that, makes the first transformation in a Lie group. Remember Lie group, like for instance, rotations, translations, those are groups of transformations, which are Lie groups, okay? So those who, took the course on advanced mathematical methods last year, they know what a Lie group is. And for those who didn't take that course, in quantum mechanics, you guys are going to see that the rotations are basically the exponential of a generator, and the generator is the angular momentum, and translations are also the exponential of a generator, and that generator is the linear momentum. Okay, so in this sense, we call this thing generator. Again, G, the generator of the canonical transformation, measures in here and here, the deviation from the identity. Okay, now, if we look at these equations, okay, these two equations, this equation here, and this equation here, okay, stopping at order epsilon, we realize that, surprise, surprise, okay, calling delta P, P prime minus P, and calling delta Q, Q prime minus Q, with a clear lack of imagination, okay, then the previous equations read delta Q equals epsilon times the Poisson bracket of Q with G, and delta P equals the Poisson bracket of itself, P, again with G, okay? So this is already interesting, right? It rings a bell. This sounds like a familiar relation, you know, between the variation of the canonical variable Q and P with respect to something. And we're going to be able to make this more precise. Okay, so this is what we see. Okay, now let's, you know, have the following observation. Let us imagine that this function g of q, p, and t, it could be anything, right? Because, you know, I could arbitrarily choose this g here to be whatever, depending on the g I choose. That will be the different, you know, canonical transformations I have. But in all cases, the g measures the deviation from the identity, right? So let us choose this g to be something that we all know and love, which is a Hamiltonian. So let us see what happens if we just choose g to be the Hamiltonian, precisely this function of q, p, and t. G is a function of q, p, and t in general. So therefore, you know, the Hamiltonian is one of these functions. Then the previous equations, you know, would become q with h of q, p, and t, and delta p equals epsilon of p with h of q, p, and t. And so now, you know, the previous two equations, they become something even more familiar, right? What do they look like? Who can tell me what, you know, where you guys have seen these equations before?
Hamilton's equation.
Exactly. These are the equations of motion. If epsilon, which is in principle, you know, the parameter that measures, you know, the deviation from the identity, is nothing but, you know, differential of time. Okay, so wait a minute, right? Wait a minute. These equations are the equations of motion. If you wish, as your classmate said, these are Hamilton's equations of motion if we choose this infinitesimal parameter to be, you know, the infinitesimal variation in time. Okay, so that means that the Hamiltonian is nothing, is the generator of the canonical transformation which we call time evolution. Okay, so in other words, evolution in time is the canonical transformation generated by the Hamiltonian. Okay, so we learned two things. First thing that we learned is that evolution in time, okay, which is, in other words, the solution to the questions of motion, this evolution in time is itself a canonical transformation. And the generator, in the sense of this G that we had before, the generator of this evolution in time is nothing but the Hamiltonian. Well, these very same words, you guys are going to say in quantum mechanics, or maybe you have already said those words in quantum physics. I don't know. Did you guys already see this in quantum physics or not? Yes. Is silence?
Yes.
Silence means yes, or silence means no?
Von Neumann density matrix, yeah?
Say it again.
You mean von Neumann equation for evolution of density matrix, yeah?
Yes, exactly. So in quantum mechanics, so this is all classical. This is obvious, right? We are talking about Poisson brackets. But you guys already know that in quantum mechanics, basically, the equations are going to be the same. You know, P and Q and H are going to become operators. And then these Poisson brackets are going to become commutators of the corresponding operators times IH bar, right? So that's basically the only change, right? And indeed, you see that in quantum mechanics, the evolution operator, which means that, you know, a state at time t is a state at time 0 times an evolution operator, okay? So this evolution operator is nothing but e to the minus I, the Hamiltonian times t divided by h bar. So exactly the same Hamiltonian. So that means, indeed, that h is the generator of time evolution. And this you will say in quantum mechanics, but you already see that this is nothing but, you know, a copy, okay, a naive, simple translation of what happens in classical mechanics. Nothing but that, okay? Now, have you guys seen this already or not?
Yes, yes.
Okay, so where did you guys see it? In quantum physics or in quantum mechanics or in both?
Both.
Okay, good. So that's one thing. So now we see that the Hamiltonian is the generator of time evolution, okay? But we also see another thing, right? Because we know that time evolution is something that we can integrate from a small infinitesimal time evolution into a finite time evolution, right? If we write down differential equations, so imagine that, you know, this epsilon here is dt, right? So if we take epsilon equals dt, then the previous equations are going to be dq equals dt. So let me just copy what I had. Q with G, Q with now H of Q, P, and T, and also dP equals dt with P of H of Q, P, and T. And we know that these differential equations can be integrated into a finite time evolution. right? So we can take these differential equations and integrate for a finite time. So exactly for the same reason, we can integrate a differential canonical transformation into a finite canonical transformation. So this can be formally, proved, justified, but I think that, just by the similarity, by the comparison with the time evolution, you already see it, right? That in the case in which epsilon is dt, that you can integrate these differential equations into some finite time evolution. So when dt was epsilon, was the parameter that was controlling a differential canonical transformation. For the same reason, you're going to be able to integrate a differential canonical into a finite canonical transformation, okay? All right, so that's one thing that we learned. What else do I want to say here? Okay, so let us formalize these things. So let me just write it down. So the same way h of q, p, and t generates in the sense of a canonical transformation, a finite canonical transformation from an infinitesimal one, since the differential equations of Hamilton can be integrated into a finite time evolution. Also, the generator G, P, Q, and T can generate a finite canonical transformation from an infinitesimal one. Infinitesimal one, which means that the iteration, repeating, right, iteration of a canonical transformation with G of Q, P, and T as the generator infinite generates, let's just make it a little shorter, with G of Q and P, Q, P, and T as the generator, generates a finite canonical transformation. So remember Lie groups. Okay? So what this says is that if we just go back here and inside this Q and P, we just replace the transformation again and again and again and again. So we just expand this thing in powers of epsilon just by iteration, right? We iterate once, twice, three times, etc., etc. This can be integrated into the canonical transformation that that this generator G generates. Okay, so this can be integrated, and this we see explicitly when G is the Hamiltonian, but this already suggests that this is true in general, and in fact you can prove that this is true in general. Okay, so that's one thing that we learn. Any questions or comments so far?
Well, I want to ask what when we do this iteration,
Yes.
what we are obtaining?
What are we? What
are we obtaining? We are iterating this thing. We are making a canonical transformation every time. But which is the end point? What is the conclusion?
Well, I mean, if you give me G, okay, and if you give me G, then this is an infinitesimal canonical transformation. And if I keep iterating, then I'm going to be able, I mean, it depends on G, of course, but then I'm going to end up with a canonical transformation for a full F. So that means, what that means is that canonical transformations have the structure of a Lie group.
So this means that from this point of view, having a generator, we can have a family of canonical transformations and not infinitesimal.
No, not a family, just one canonical transformation. Exactly the same way, when you have the angular momentum, okay, and you iterate the angular momentum, you generate a rotation. It's the same.
Well, but I see it clearly with the Hamiltonian, but not with a general G.
Of course, yes, yes. Here I agree with you, okay? I didn't show that this is true in general. I just showed that these equations, in one particular case, you know what the answer is when you integrate them. In the particular case in which G, coincides with the Hamiltonian, you know the integration of these differential equations because that's what we call time evolution. Okay? Now, I didn't prove it. It can be proven, but I didn't prove it that this is also true in general. But now it is relatively easy to accept, right? I think that, if you can integrate these equations when the Hamiltonian is G, why shouldn't you be able to integrate this equation for any general G?
Okay.
That's the point I'm trying to make.
So you put here some G in concrete, having a Hamiltonian angular momentum or something like this, and you get a canonical transformation in general.
Can you repeat again?
And we have proved here, if we put a Hamiltonian, we have the time evolution. We can put here angular momentum, and if we put here anything else, we have another canonical transformation.
Yes. So for instance, if instead of the Hamiltonian, you would put for G the angular momentum, then this delta Q will be a rotation.
Okay.
That's the idea.
Okay, thank you.
Okay, now we still can see other consequences of these relations, right? And let us look at those consequences. What happens if a canonical transformation with generator G of Q, P, and T leaves the Hamiltonian invariant? Right? So here we are already asking a question that smells a lot like Nether's theorem, right? If we have a transformation which leaves the Hamiltonian invariant, it's going to be, of course, Nether's theorem in terms of the Hamiltonian, not in terms of the Lagrangian, because now we are basing all the argument on, you know, Q's and P's and Poisson brackets, right? So that's a Hamiltonian, is a Hamiltonian formulation. So what happens if we have a generator? So we make, therefore, a canonical transformation, which leaves the Hamiltonian invariant, okay? Okay, so that means, so let's call this, let us call a general observable. So a given observable. I'm going to call it U, okay? Which is going to be a function of Q, P, and T. Soon this U will be the Hamiltonian. But let's think that we have a U, any U, okay? Now this is, if we make a canonical transformation, we go from Q to Q prime, which is a function of Q, P, and T in general. P goes to P prime, which is a function of Q, P, and T. So therefore, that means that this is a function of Q prime, P prime, and T, a function of Q prime, P prime, and T, and then also T, okay? So let's imagine that this thing, which in principle is going to be a different function of Q prime, P prime, and T, after I make a change of variables, the function as a function of the new variables is not going to be exactly the same function as it was before. It's going to be a new function in general. But imagine, let's assume that U prime equals U. Okay, so that means explicitly that the function, in fact, is not different, it's the same. So U prime of Q prime, P prime, and T is exactly the same function of U of Q, P, and T. In other words, U is invariant. Okay, let's imagine this situation. Well, then we can compute the variation of U when the Q's, you know, are varied this way, right? So what is the variation of U? So this is partial of U with respect to Q, delta Q, plus partial of U with respect to P, delta P, right? Because this canonical transformation, what it means is that, you know, Q prime minus Q is delta Q. There's been a change, right? So, and this means that P prime minus P is delta P. So that's the delta Q and delta P I'm talking about here, as before, right? But we know that delta Q is epsilon partial of G with respect to P, right? The generator of the canonical transformation. And we also know that delta P is minus epsilon partial of G with respect to P. So in other words, if I, you know, use this equation and this equation in here, what I find is that this is nothing but epsilon times that observable U with the generator G. Okay? This is general. For any observable U which remains invariant under a canonical transformation. This is always true. Puff. This is it. Now we are going to go back to this statement. Imagine that the Hamiltonian is invariant. So that means, let's take now the previous result for the Hamiltonian. So U is now the Hamiltonian itself. If U is now the Hamiltonian itself, and obviously, I forgot to say one thing here. If U prime is the same as U, this is of course 0, right? So that is 0. 0 equals this. So if U is the Hamiltonian, then 0 equals the variation of the Hamiltonian because it doesn't change. And this is epsilon times the Hamiltonian Poisson bracket with the generator. So if this is 0, that means that H is invariant, the Hamiltonian is invariant whenever the Hamiltonian with the Poisson bracket, whenever the Hamiltonian and the generator have a vanishing Poisson bracket. Okay, so this result, okay, in quantum mechanics is H is invariant under the transformation generated by G if it commutes, right? This is an result that you guys have seen, right? That asymmetry of the Hamiltonian is equivalent to the statement that the commutator of the generator of that symmetry with the Hamiltonian vanishes. Have you seen this result also in quantum mechanics?
Yes.
Okay, so as you see, is a result that actually comes from classical physics, okay? And so we're still going to see something else. So G is the generator of a symmetry, right? Can be the generator of a symmetry, right? Of a transformation which leaves the Hamiltonian invariant. Examples are examples. Examples are rotations, translations, etc. All those continuous transformations, right? Leaving the Hamiltonian invariant. I forgot something here. So let me just, okay, sorry. So I want to add here, a couple of words. G can be the generator of a symmetry in the sense of Lie groups. I want to say this. In the sense of Lie groups. And now comes the examples. I forgot this. Examples. So rotations, translations, etc. Depending on the problem, you may have other symmetries. Okay, leaving the Hamiltonian invariant okay, so this we have now the generator of a symmetry, and it's a symmetry because it leaves the Hamiltonian invariant. Okay, and now if this generator, G of Q, P, and T, is the generator of a canonical transformation leaving H of Q, P, and T invariant. Now, if we have this, let us do the canonical transformation corresponding to time evolution, because we saw that time evolution is also a canonical transformation. So let us do the canonical transformation corresponding to time evolution on precisely this generator. So this generator G, right? This generator, which is a generator of a symmetry, is a generator of a canonical transformation, a certain canonical transformation, which leaves the Hamiltonian invariant. Now we want to do on this observable G, on this function G, the canonical transformation, not generated by itself, but the canonical transformation, which, you know, is equivalent to time evolution. So we want to look, you know, what happens when we, you know, evolve in time this G. And that we know, because we know that the variation of this observable with time, so a function of Q, P, and T, is the Poisson bracket of itself with the Hamiltonian plus the explicit time evolution, the explicit time dependence, right? These are, remember, these are the equations of motion, you know, derived from Poisson brackets. We already obtained this equation when we were discussing Poisson brackets the first time, right? So if we look at the time evolution of G, where G happens to be not any function, but G happens to be the generator of a canonical transformation which leaves the Hamiltonian invariant, then if G is the generator of this canonical transformation leaving the Hamiltonian invariant, in other words, of what we call a symmetry, then we know that it commutes with the Hamiltonian in quantum language, or we already see that the Poisson bracket with H is 0. Okay? But if the Poisson bracket with H is 0, then the derivative of G with respect to T is nothing but the explicit time of G with respect to T. And if G of Q, P, and T does not depend explicitly on time, is a constant. So in other words, conclusion, generators of symmetries, example, P, linear momentum, angular momentum, etc., are constants. Are constants if they leave the Hamiltonian invariant, right? Are constants. So let me just, I need to write this thing fully, okay? So let me just, I'm gonna write it in the next slide. I just ran out of space. So I'm gonna write it in the next slide. Generators of symmetries are constants. Example, linear momentum, angular momentum, etc. And they are generators of symmetries because they commute with the Hamiltonian or leave the Hamiltonian invariant. That would be in quantum language, or, you know, the Poisson bracket with the Hamiltonian is 0. Okay? So, as you can see, all this formalism of canonical transformations has allowed us to reformulate Noether's theorem in terms of the Hamiltonian. And essentially what we find is exactly the same that is being said in quantum mechanics by, you know, the simple replacement of taking the Poisson bracket and writing I times the commutator. Well, actually, it's the other way around. The commutator is I times the Poisson bracket. Okay, so all this structure is already, you know, inside, it's already underneath the canonical transformation formalism. Okay, that's a good point to stop and ask questions or comments if there are any.
Santi,
Yes.
Yeah, I had the question because I did not take the course on advanced mathematical methods,
Yes.
and I do not know what Lie groups are exactly, and I do not understand what what is their importance.
Okay. So, but did you take the course on quantum mechanics or
Yeah,
quantum
sure.
physics? I don't know which one it is. Okay.
Yeah.
So in quantum mechanics, so let me try to make it as familiar to you as I can. Okay. In quantum mechanics, who is the operator that makes a rotation, of an angle theta along a certain axis n? So how you make a rotation on a ket, say on psi?
Mm, maybe with the angular momentum operator.
Yes, but so what is it? Is the exponential, right?
Yeah, of minus I,
Yes.
and
J,
then you
the
get
angular momentum, times n times the angle on psi, right? Okay, so this is a Lie group. Rotations are a Lie group, and that means that this function is a continuous function of a parameter, which in this case is the angle theta. Okay, so the elements of the group are functions of a certain parameter, and when the parameter is very small, this is the first correction to the identity. So the first correction to no change whatsoever is the generator. So what you can see, these are mathematical properties of a Lie group. All Lie groups have these properties, right? So all the elements of the group are functions of a parameter. The elements are the exponentials of the generators of the group. And in the case of rotations, the generator of the rotation is the angular momentum. So this is the minimum you should know about Lie groups.
Okay.
All right.
Okay, thank you.
So as you can see, for instance, time evolution is also the exponential of the Hamiltonian times time. And so the Hamiltonian is the generator of, in this case, would be time translations, right? That would be a translation. And if instead of a rotation, here it would be a translation, a space translation, then it would also be the exponential of, in this case, would be the linear momentum times, a parameter would be the translation, the space translation that we have. So rotations, translations, and time evolution are Lie groups. In particular, time evolution is the same as time translation. I don't know. I mean, those who have taken advanced mathematical methods, is there anything about Lie groups which is important that your classmates should know and that I forgot? Hello?
I don't think so. No.
Yeah, okay. So I think this is the minimum you should know. And keep it in mind when you guys discuss all these things in quantum mechanics, which I'm sure you're going to discuss. You say that you have already discussed them, but I'm sure that you guys are going to discuss them much more in the future. Okay, now any other question or comment regarding canonical transformations and different reflections about those?
No.
No other question?
Well, I have one
Yes.
question. Given asymmetry,
Yes.
there is only one possible generator, or there could be more?
It depends on the symmetry. For instance, when we're talking about, it depends on the symmetry, depends on the structure of the Lie group. What kind of Lie group are we thinking about, right? For instance, if we think of the Lie group, which is time translations, there is only one generator. And the reason is because time translations only has one parameter, which is the translation in time. Time is the only parameter, so that's the thing that I vary, right? So the number of generators has to be the same as the number of parameters of the group. And the number of parameters of the group is the number of, the number of numbers, so the amount of numbers that I have to fix to define an element of the group. So again, back to the example. Time translation, there is only one parameter, time. Therefore, there is only one generator, the Hamiltonian. Okay? Now, space translations. How many parameters do I have to define a translation in a space? Three, right? I mean, if you guys don't know, go back to when we were discussing, the Galilean group, right? We also identify all the parameters of the familiar symmetries. So space translation, right? So space translation, I can make a translation in the 3 dimensions of a space. So that means 3 parameters. And indeed, the generator is the linear momentum, and the linear momentum is three objects, P sub x, P sub y, and P sub z, right? So the 3 components of the linear momentum P vector. Now, rotations. How many parameters do I have to define a rotation in a space?
Also 3.
Also 3, right? For instance, the 3 Euler angles. Or for instance, here, I'm telling you that there are 3 because this little n, okay, so let me just make this thing more specific. Here, if J is the angular momentum, it looks as if I have 4 parameters, 3 components of n, and the value of theta, the value of the angle. But this is not true. Why not? There are no 4 parameters, 3 plus 1. There are only 3. And why is that?
Because theta is
it has to be normalized.
You guys were speaking all at the same time.
Sorry.
So I heard theta blah, 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 and then normalized. So one of you should say something. Say something.
I said that because theta is infinitesimal.
No, this is not. No. I mean, infinitesimal.
No, sorry.
Infinitesimal is still a variable. Okay, this theta is infinitesimal, but it's still a variable. Okay, it's not fixed. So this cannot be the reason. If this was the reason, it would be theta is 1, n is 3, so that would make 4 parameters. And we know this cannot be true because there are only 3 Euler angles. So why is the reason?
I said that n is a unitary vector, so it has modulus.
Exactly. N squared is 1. This representation requires that n squared has to be 1. Exactly. So that means that n squared is not 3 components, but it's only two components because the sum of the squares has to be 1. So that already squares. That matches the counting that we had. Okay, so that makes 2 and 1 is 3 parameters, and those are the Euler angles. So again, you see that the number of parameters matches the number of generators. This has to be. This is always the case for a Lie group. Anything else?
In this case, the generators of the rotations would be JX, JY, and JZ.
Yes, absolutely. J.
Okay.
J. Yeah. So this. Yeah. I mean, I didn't, make it explicit. I didn't spell it out, but because I thought that this was obvious. But no. J equals JX, JY, and JZ. Absolutely. Okay, other comments or questions? And H bar. There should be an H bar here. In quantum mechanics, you always put an H bar. I mean, yeah, okay, I'm sorry. I mean, for me, H bar is always 1. Okay, so that means that there is an H bar here. So that's a question of units. Yeah, for me, H bar and the speed of light is unity. So I tend to forget about H bar. Okay. Other questions or comments?
No.
Okay.
Question, sorry. Thank you.
All right. So now we're going to make a big change. Okay. Initially, in the list of topics that I wanted to discuss in this course, now if you guys go to the what do you call this thing, in the Guia du Sen or something, you guys are going to see that the next topic to the next chapter was the Hamilton-Jacobi equation. But I'm gonna skip that now. This year, because of all this COVID thing and all this different situation, I'm gonna skip this subject, and I'm going to move right away into classical field theory, which is the thing that comes after the Hamilton-Jacobi equation. So I'd rather do classical field theory, and only if at the end of the course we still have some time, I will go back to the Hamilton-Jacobi equation. Okay, Hamilton-Jacobi equation is also interesting because it's the Hamilton-Jacobi equation what actually led people like Schrodinger and Born and other people, to develop quantum mechanics. So I mean, today we don't, present quantum mechanics that way. But 100 years ago, when these people were trying to invent quantum mechanics, the thing that they had in mind was actually the Hamilton-Jacobi equation. So I think it has some interest. But just in case we run out of time, I'm going to skip it at this point, and I'm going to move to classical field theory. And if at the end of the course we still have some time left, I'll go back to Hamilton-Jacobi.